Okay, so let's continue with the second presentation from Mihai Budiu, who is going to talk to us about building a streaming incremental view maintenance engine with Calcite. The mic is on you, Mihai.
Thank you. Thank you, everyone, for listening to my presentation. All right, so let me start by explaining what is incremental computation. So let's say you have a program P, and you feed it some input I, and it gives you some output O. And then you make some small change to your input by adding, let's say, a little delta to it. And hopefully, the output isn't too different. What you would like to do is to reuse the computation you've done when you computed the output for the initial input. In general, this is a very hard problem, but it works really well for databases. Why? Because databases have a natural notion of a change. In a database, think P of being a query, I being a set of tables, and delta I is a change that you apply to your tables, which is what a transaction does. And O, you can think of O as being a view. And why would you want to compute incrementally? Because often the changes you apply to your database are much smaller than the database itself. And hopefully the output changes in your views are also much smaller than the views themselves. So maybe you can do this much more efficiently than if you recompute the entire query over the new input. So in databases, this is called incremental view maintenance. All right, so this talk has two parts. The first part is a theoretical part, and it's relatively simple as theory goes. It's much simpler than the relational algebra. But once you have the theory, it's very easy to build on top of it. And we built a full implementation using Calcite, which I plan to describe in my second part of the talk. So if you want more details, this will be published at VLDB this summer. And we're still working on the final version of the camera ready, but it will be available. The deadline is next Monday. So the paper will be available if you want to read all about it. And I have to acknowledge my co-authors. I'm only presenting on behalf of the team. All right, so what is this about? It's about a very simple language to describe streaming computations, which we call DBSP. DB comes from database, but DSP comes from digital signal processing. It's a pun because it's inspired by signal processing. The language only has 4 operators, and it allows us to rigorously define what incremental computation means for DBSP programs. But more important than a definition of the incremental computation, we actually have an algorithm which takes an arbitrary DBSP program and converts it to an incremental DBSP program. And this algorithm is heuristic free, so it's actually recursive on the program structure. And the language will be too useful if you can't use it to implement what you want. We also have a recipe for implementing a very large class of queries in the DBSP. It turns out 2 of these operators are necessary to implement all of SQL, and 2 more, which I'm not going to cover today, are used for recursive queries. So how expressive is DBSP? It's actually really powerful. You can model in DBSP almost anything you can do in a normal database. The relational algebra is included in DBSP, but you can compute on sets, bags, and multisets. We can handle nested relations, not only one level. We can do arbitrarily deeply nested relations. We can do aggregations. This is all in the realm of SQL, but we can do also recursion, monotonic, and non-monotonic, like Datalog does. We can do stratified negation. And we can also express streaming computations, like joins or window aggregates, like languages like SQL. And the beauty is, because we have this algorithm which incrementalizes any query written in DBSP, we can automatically get incremental view maintenance for any query written in any of these languages. Okay, so I'm going to explain now how this is possible. And I hope this will provide a fresh perspective on and it will unify 3 different paradigms. One is streaming computations, one is database, and one is incremental view maintenance. I claim these are actually the same thing. Okay, so let's start by defining what a stream is. This can be very mathematical, but let's think of a stream just as an infinite vector of some values of some type A. And let's assume that the type A has a plus and a minus operation and also a 0. The plus and the minus, think of them as applying diffs. So the minus allows you to compute differences between 2 values that are stored in this vector. Now, a stream operator is a function that computes has an input a stream or multiple streams and outputs a stream. And I'm going to use these cute diagrams, which are inspired by signal processing, where arrows are streams and boxes are operators. So here you can see a unary and a binary stream operator. So far, so good. All right, so now how can we build computations on streams? I'm going to introduce the first operator in DBSP, which is the lifting operator, which is a very simple operator, which you've all seen. It looks like the map operator. Given a function that operates on scalar values, it just lifts this function to operate on streams by applying the function to every element of the stream. So I hope that there's nothing mysterious about lifting. Another thing you can do, if you have two stream computations, you can chain them together in a data flow graph. So that's how we can compose more complicated computations on streams from simple primitive operations. All right, now the second operator and the last one I'm going to introduce today is the delay operator, which is also very simple. The delay operator takes an input stream and outputs the stream delayed by one time unit. The first time unit it outputs a 0. Remember, we expect that the data types we operate on have a natural notion of a 0. And afterwards, it outputs the stream as it's seen it. And we use this notation z to the power -1. This comes from the digital signal processing. It's something related to the z transform. But whenever you see a z to the -1, just read delay. Okay, so now let's build some circuits. Oh, so by the way, I forgot to mention, I really welcome questions even during the talk. So feel free to interrupt me at any time. In fact, I'm asking whether you can guess what this particular circuit is doing. Does anybody want to volunteer or guess?
I'm going to guess that it doubles, it unions a stream with its time shifted with things delayed by one item.
That's correct. So what it does, it actually takes the input stream and delays it, but also negates every element, and then it adds it to the stream itself. So if you look what it does, it actually computes the deltas between consecutive elements of the input stream. So let's call this a differentiator or something that computes deltas given a stream. And we'll denote this whole box as D from differences. So given a stream of values, this computes the differences in the values. So for example, if the stream of integers 1, 2, 3, 2, the deltas will be 1, 1, 1, -1. The first value is copied unchanged, as if there was a 0 in front of it. Okay, so this is an operator you can build using the components we described so far, which computes deltas. Now, here's an even simpler operator, but weirder looking, which only has a delay and a plus. So let's try to guess what this one is doing. So if you look at it, what it does is it has some output and it adds to the output, the previous output. That's what the Z, the delay gives you. It adds the current input. All right, so if you write this, what you get is that the Tth output will be the sum of all the inputs up to T. So it's a prefix sum of the input stream. Okay, it's let's call this integration. It really is a discrete form of the integrals in mathematics, but don't be worried about it. It's just the sum of all the inputs you've seen so far. So we call this operator I from integration, and it's the inverse of the previous operator. If you have a stream of changes, like produced from the previous operator, this one will reconstitute the original stream. So these two operators are inverses. They have this nice mathematical property that if you chain them, you get nothing. You get the identity function, just a wire. Okay, so everything looks very simple. All right, so now I'm going to make a very bold claim. All the databases you've seen so far are streaming databases. And I'm going to explain why. So, you know, people think of streaming databases as being an exotic object and build custom engines. And I think I claim you don't need to do that. All right, so let's take a database, which is just a set of tables. All right, and consider a committed transaction to the database. What is a transaction? Is a change that you are applying to your database. Now, we all know that transactions have the very nice property that they form a linearized stream. So you can think of the transactions as forming a stream. T0 is the first transaction applied to your database. T1 is the second one, and so on. All right, so that the tth transaction is the one that you applied after t operations. Now, you can think of your database as also forming a stream. It's a stream of snapshots. All right, so DB at time 0 is the database when you started. It was probably empty when you created it. DB at 1 is the database after you applied the first transaction, and so on. And there's a very simple relationship between those two objects. The database stream is the integral of the transaction stream, where the integral is the previous operator that I've shown you. So the database at time t is the sum of all the transactions you've executed so far. All right, now let's shift our attention to views. What is a view? A view is essentially defined by a query. So here's a view defined in SQL. And it's essentially just a function of your database, right? So given Q, let's say Q is a function, and given the database, what is a view? It's something that evolves as your database evolves. So it's nothing but a stream of values. Okay, so if you consider your database stream, remember the set of snapshots of your database, for each database snapshot, you have a corresponding view. So the view at time 3 is the function applied to the database at time 3. But this is nothing but our lifting operator that we described previously. We apply the lifting operator to the database stream to get the view stream. So computing views is nothing but lifting functions over database streams. Okay, and now I'm going to define for you what incremental view maintenance is. This is actually a new definition. It looks a lot like the old definition, but it differs in a very subtle way, which I'll point out. All right, so this is the same picture as before. So you have a stream of databases, and you apply a function, a query to each database version, you get a version of the view. Remember, the database itself is the integral of a stream of transactions. You just sum up all the transactions. So we just chain those two operators. And now we'll do something symmetric on the output. We'll apply a differentiation operator, and we'll get a set of changes to the view that we want to maintain. And I claim, so we denote, given a query Q, which defines the view, we'll denote this by Q to the delta. And we'll call this the query that incrementally maintains the view V. So let's think what we want to do. Given a set of transactions, we want to compute the changes to the view directly. That's what we call incremental view maintenance. This is not exactly like the traditional definition. The traditional definition would be missing this last differentiator. It would look like this picture, really. But I claim this is a much better picture because it's composable. So the same way that Julian pointed out that SQL is all held by tables, everything is a table. You can substitute tables with queries or views and so on. In this definition, everything is a change. Inputs are changes and outputs are streams of changes. And this makes it compositional. Now we can compute, we can talk about composing computations on changes. And let me explain why this is extremely powerful. But before I do that, I want to point out that the incremental version of a query is no longer a query. It's a streaming system, which has internal state, right? So given the query that I've shown you here before, this query which defines a view. There's a question?
Yeah, can I ask a question? I'm so sorry.
Yes, please.
In the previous slide where you had the diagrams and it showed the whole thing, can you explain the purpose of the D, the differentiator on the end again? What
Okay.
that does?
All right. So the question is, why do we do the differentiator here? Because I claim that what an incremental view maintenance engine should give you, it should tell you whatever changed in your view for the last transaction you applied. And it should do that because the changes tend to be small. That's the way how it can communicate to the outside world what is interesting and new about the view. Usually databases let you query the view, but that is expensive because the view might be large. But if the database reports to you what the changes are in the view, then these are hopefully much smaller than the view itself. Okay, so we claim this is this is the right API to define incremental view maintenance. But as I'll show you, you get many more benefits if you approach the problem in this way.
This, can I interrupt?
Sure, of course.
So had this insight already. And so this stuff, it's not much used, but it is in Calcite. There is actually a relational operator called delta that represents differentiation of relational algebra, and another relational operator called sigma that represents integration of relational algebra. It's not based on, you know, your kind of circuits. It's more wired to relational algebra, but there's a very similar concept in Calcite already.
Oh, that's great. I actually didn't know. I'll show you how we use Calcite, and we convert Calcite representations to our own representation, but maybe I didn't need to do that if I knew that the operators are available. But okay, all right. But let me show you now. So this is an acute insight, but it's still not useful. I'll show you why it's very, very useful. So, but let me finish this point. So if you take a query, which is just a pure function, the streaming version of the query, the incremental version of it, maintains state. So it needs to run forever, right? So because the one output might depend on all the inputs you've seen so far. You can't compute an output just based on the current input. It's not just a lifted query. So it usually, the incremental version of operator is stateful. And where is this state stored? It's actually stored in the delay operators. If you look at both high and D, they have a delay. And the delay is the one that remembers what happened previously. So the state is confined to exactly one operator in the streaming model. And this can be very useful if you want to do fault tolerance or checkpointing or even state migration. But I'm not going to talk about that too much. All right. So there's two properties of operators which make this view of incremental view maintenance much, much more useful. So first of all, the first property is that if your operator is linear, which means it has this property that when you apply it to the union of two collections, think of plus being a union, you can apply it to each collection separately. Then for such an operator, they are equivalent to their incremental version. So you actually don't need to compute anything. Why is this better, all right? So the top picture is the definition I showed on the previous slide, where you integrate, then you apply the operator, and then you differentiate. And if your operator is linear, it says that you can skip the integration and differentiation. You can just apply the operator directly to the transaction itself. And this is much faster, right? Because it's a speed up, which is the ratio between the size of the database and the size of the change. You don't need to build the database to compute the output. And let me give you an intuition. Look at this query, right? So this query happens to be linear. It's just a filter query. And it's linear because it's shardable, right? If you have your table sharded into pieces, you can apply the query to each piece separately and union the results. That's the intuition of what it means to be linear. And the funny thing is that in the relational model that I'm going to show you, almost all the operators are almost linear. I'll show you how. And so this means that if you want to do relational algebra, we can do incremental view maintenance extremely efficient. Okay, now the second property, which is interesting, and this is really the crux where compositionality kicks in, is that if you want the incremental version of a composite query, it's enough to compute the incremental version of each of the components of the query. Okay, so and this might seem surprising, but I'll show you the whole proof is a proof by picture. So the top row is the definition of the left-hand side, right? So what is the incremental version of a query is integrate, apply the query, and then differentiate. And now what I do is I'm sneaking in the middle. Remember, D and I together, they mean nothing. So I can sneak in this composition of D and I and then reassociate because this is just function composition. Function composition is associative. And I get the definition on the right-hand side. So the proof is trivial, but it's actually the key why you can take any arbitrary query plan and incrementalize it by incrementalizing each component of the plan independently. So this means if you have a language in which you know how to incrementalize each primitive operator, we can incrementalize any arbitrary query based on that language. And amazingly enough, this also extends to recursive queries. The things become a little more complicated, which I don't think anyone knew how to do so far. So this is also an interesting insight. Okay, so let's do this on a database. And the first problem when you try to apply this directly to the database is that it doesn't have a plus and a minus and a zero. But fortunately, there's a trick you can do to the database, which is an old trick. It's been at least 15 years old, which is to replace each table with something called a z-set or a z-relation. And essentially, you add a weight to the row, to each row. Each row has an integer weight. In fact, this generalizes to real weights or even other structures might work. But let's stick with integers. So this tells you how many times the row is present in a table. Okay, and if a row has a positive weight, then the row is there many times. If the row has a negative weight, it means we actually would like to think of this row being removed from the database. This reminds me of this joke. There's a house and 2 people come in and 3 people come out, and then they ask some scientists, some people, what happened. So and the social scientist says, obviously there was somebody in the house. Then the the doctor says, they multiplied, and that's why 3 came out. And the mathematician says 1 more person will go inside, and then the house will be empty. And we actually take this pure mathematical view, and it works very well. I'll show you how it works very well. All right. So obviously, you can represent traditional database tables using z-sets. Just make sure that h weight is 1. But the z-sets are very good because they can generalize not only tables, but they generalize multisets, and they also have a very nice structure. And there's an operator that we need to add, the distinct operator, which takes a z-set and makes it into a set. What it does essentially is throws away all the negative weights and makes all the positive weights 1. So it's a very simple operator. You can see how it works. Okay, so now armed with this operator, this is a simple table which is, you don't expect it to read, but it shows you how every relational algebra operator can be implemented using computations on z-sets. So for example, to do union, you just add the z-sets and then apply distinct, right? Because the union could introduce duplicates and the distinct will throw them away. And the difference is similar. It's at the bottom. So that's except. So now, given any relational algebra query, we can define a circuit that computes this using z-sets. So if you look at these operators, many of them require distincts. Okay, the blue circles show distincts. But the nice thing is that all the other computations involved in building the relational algebra require linear or something called bilinear operators, which I'll talk about very briefly only. The join is actually a bilinear operator. It's a generalization of a notion of linearity on operators would have 2 inputs. So this is how a join looks. So the join is more complicated, but if this looks too complex, don't worry too much, I'll explain it. So on the picture on the left side, you have the incremental version of a streaming join, right? So there's a join. Actually, I'm displaying a Cartesian product, but the joins works exactly the same way. So you need to integrate the inputs and then differentiate the output. That's the definition of incremental version. And on the right-hand side, we have the optimized implementation of it. And what does this one do? So let's think about it this way. If you have a join and you add an element to the left collection, what changes in the output? Well, this element you added to the left collection has to be joined with everybody in the right collection. Okay, so that's what happens in this multiply operator on the bottom right of the top. The little a is the change to the left collection, and this one b is the integral of the right collection, which is everything you've seen so far in the right relation. So that's why you have this multiplication here. There's a symmetric case to be made, a symmetric argument. When you add something to the right collection, you have to join it with everybody in the left collection. And obviously the 2 changes have to be multiplied themselves, and then you sum up the results. And you've seen maybe this formula for incremental joins. This actually corresponds directly to the circuit. So if you squint, you will see how the circuit is translated into this formula on how to compute incrementally joins. If you haven't seen it, don't worry too much. It's not particularly deep. But the point is that this incremental implementation on the right is more efficient than the one on the left, again, with the factor, which is the ratio between the size of a collection and the size of the change. So the computation is not as just the size of the change, because it might potentially join with a large relation. You have to integrate the 2 relations, but still it's better than doing the thing on the left directly. Okay, So this is the theory. So now what can we do with the theory? So first of all, we built a library, which is called the DBSP library, which is open source with an MIT license. It's a Rust library, which supports everything you've seen so far. So you can build all these circuits, including recursive circuits, and it runs multi-core, and it's pretty fast. So we benchmarked it against Flink. We have written the queries by hand in Rust, so not using the compiler. I'll explain why in a minute. And we can beat Flink by a factor of 3 to 5. Smaller is better in this picture. Don't worry about it too much. But we are also building a sequel to DBSP compiler, which is based on Calcite, and it's also an open source project, also with an MIT license. And essentially, it takes SQL and generates Rust programs that link to this DBSP runtime. So how do you describe streaming systems in SQL? And not streaming, incremental streaming systems. It turns out you don't need to do any change to SQL at all. You just have some create table statements. Each table becomes an input. And you have some create view statements. Each view becomes an output. And the queries that define the views, they become the data flow graph, which is translated using the recursive rules that I've shown you in the previous picture. So that's how you get a streaming engine. So the compiler flow is, pretty simple. We use Calcite to parse this data definition language. So everything is a DDL, right? We define tables and views. That's all. Then we convert this to a lower level. We optimize. We have a set of optimization rules. And then we convert this to a circuit using the rules I described. And then we incrementalize the circuit using this recursive traversal, where we replace essentially each operator with this incremental version. This outputs a Rust source file, which is compiled using the Rust compiler, using the DBSP runtime, which implements all these streaming operators. And then we also link it with the SQL runtime library, which implements the semantics of all the SQL built-in functions and operators. So there's a question in the chat. Yeah, we have a backend to Calcite, which essentially generates a Rust implementation of these queries, if I understand the question. And then what you get is an executable, and this executable is a function to which you supply a change, and it gives you the corresponding change in the view. So it's a streaming system that runs forever. It runs in memory right now, but you give it a change, it gives you a change. It's a very simple contract you have with this system, and they're very, very clear. And this works for any SQL query you can write in Calcite. Almost. So this took about 10 months to implement. And now is the moment to thank you guys, because it's unbelievable to think that one person could implement a full SQL compiler for incremental view maintenance in 10 months. And it's only possible because this community has built this fantastic tool, which is, by the way, really well engineered. It's a joy to work with. Documentation could be a little better, but because it's Java, it's easy to discover, and it's open source. You can, in the end, discover how it works. So we built all of core SQL. We built some window operators, and we're not finished. And we will want to add some streaming operators, but we can do actually a lot already with just pure SQL. As long as you want to do just incremental view maintenance, SQL is all you need. And right now, so let me make a very important point. What kind of incremental view maintenance plan do you get? You get exactly the plan that your optimizer told you to execute. All right. So when you optimize an ad hoc query, you have this luxury of looking at the database. Maybe you have statistics about the tables. Maybe you've run queries in the past, you know something. But when you build an incremental view maintenance system, logically, you haven't seen any of the data. So you have to build your plan before you know what the data will be. The data will run forever, So data might change, so you don't have any statistics. So we can't build a very smart planner for our streaming system. And what we do is we just use the traditional optimizers in Calcite, but without statistics about the data. And right now we use only a few small set of rules using the HEP planner, but that's probably an interesting space. I think there's not much literature about how to do optimizations of plans for incremental view maintenance. So there's a question in the chat. So indeed, what we do is we have our own intermediate representative for these circuits, but it is built by recursively traversing the rel nodes representation of a query plan, and then we generate the circuits, and then we optimize the circuits a little bit. But most of the heavy optimizations have to be done on the SQL representation, on the rel planner, on the rel nodes representation. So how well does it work? So we can run all of the SQLLogicTest suite, which has 7 million tests, and only 2 failed. And it's a narrow test suite, but it exercises everything in core SQL. And we don't do statements like create index and stuff like that. All that we send to a database, but all the queries, we get the data from the database, we stream it through our queries, and we check the result with the reference outputs, and it all works. And we are now converting the Postgres test suite by hand. We have to rewrite it manually because Calcite doesn't support many of the weird Postgres features. And sometimes we find subtle semantic differences. So these are the 2 tests from SQLLogicTest that fail. The first one fails because an overflow and multiplication, which by the definition they shouldn't exercise. But essentially in MySQL, for example, int times int is big int, but in Calcite is int. So that's why these 2 can give a different result. And the second one fails because of division by 0 at compile time, which Calcite thinks is a non-nullable result, but some databases think should evaluate to null. So this brings me to the problem of syntax and semantics in SQL. I filed an issue about the first problem here. So the DDL and bubble parsers are kind of complementary, right? Now you can, if you just want to use Calcite off the shelf without changing the parsers, but we'd like to have both. So it'd be very nice if you could stack them somehow. We'll probably have to roll out a combination of the 2 ourselves. Because we need the DDL language because that's how we define the views and the tables, but we need the bubble parser because we want to support the richness of the functions it supports. And languages like MySQL, they are not parsed by the DDL parser existing, like primary key and signed and div instead of slash. So there's many SQL dialects that each of them is different in a slightly different way. And the semantics is also an interesting point. If you read the specs, SQL leaves many behaviors undefined or semi-defined. And I'm afraid the dialects don't even respect the standard. There's one thing that you want to have different in a streaming world is if you run a pipeline continuously for days or months, you don't want runtime errors. When you write one ad hoc query, it's okay if it says division by 0. But if you want this to run forever, you don't want to after 3 months to discover that the pipeline crashed and because you fed a 0 in the wrong column. So ideally, we would like all the computations to be total functions. So we prefer a general semantics where division by 0 returns null to crashing. And also for I'm not sure it's a fundamental reason, but right now the code is fully deterministic, so we don't support pipelines where you can call random or now. These, if you want to compute on times, you have to feed as input data. So you must have a table or an input stream which contains the current time, and then you can compute on them. But I'm hoping that this conversion can be performed automatically, but we haven't done it yet. And there's one more thing I want to point out is that Calcite has a notion of semantics of what it's compiling. It's very flexible and very extensible, but it's not infinitely extensible. For example, Calcite does constant folding. If you ask it to. There's an optimization pass which does constant folding. And sometimes you would think, for example, why do you care about Calcite? Let Calcite just give you the plan, and you can decide at the runtime if division by 0 is an exception or null. Well, unfortunately, if the expression is constant, Calcite will decide at compile time. So the compile time evaluation of an expression has to give the same result as the runtime evaluation of the same expression. So you don't have full freedom in the runtime to choose the semantics of SQL. It has to agree with what the compiler has said. And that's why I'm asking, I'm fairly new to Calcite. I've never used it before I started this project. For example, in Calcite, the day of week function returns 1 for Monday, but in Postgres it returns 0 for Monday. And for a while, I thought that the notion of dialect, SQL dialect, would solve this, but it turns out the SQL dialect is something that Calcite uses for output, for generating, for using JDBC. Maybe it would be nice, I don't know if it's possible, if Calcite had the notion of an input dialect. So it said, I would like this program I'm compiling to behave like a Postgres program. And then this, when you say that, this will automatically switch the type inference rules, the set of data type support, the expression evaluation rules, and all the functions supported to really match Postgres. But I don't know, because this I need you to thread this to the whole infrastructure. Yeah.
Yeah, you've raised many good points, and I can't reply to all of them. But it does have it has the notion of dialects when it's generating SQL. That's the SQL dialect relates to generate the SQL it's generating. It does have another concept which is relate to the SQL that it's parsing. So it does have the concepts of dialects at both ends. And you know, the day of week function, that's kind of an omission. The way we model that is just to say that if you're using the Postgres day of week function, it's just a different function than the Calcite day of week function. We have a few cases there where functions have just different behaviors, and so we just model them as two different functions with the same name, and you choose which one you want to use. But it gets really complicated if you are, for example, running a Calcite query that's joining data from Postgres to MySQL. So we have to have if someone says day of week, if someone uses the day of week function, we have to have a really clear semantics of whether that this means Calcite's day of week function or Postgres' day of week function, because we still need it to have well-defined syntax, even if we decide to push it down to MySQL.
I see what you're saying. So my use case is emulating an existing system, but what you want is interconnect multiple different systems. Yeah,
but your use case is totally valid, and we should support it. Yeah, this is all great feedback.
Okay, so this is my last slide. So what have I told you today? I told you that streaming systems are systems that run forever. And then you should think of every database being a streaming system. A table is just the integral of a stream of changes, and a transaction is the delta of a database. So integration and differentiations are fundamental operations in databases. They are fundamental operations in incremental view maintenance. The right definition of incremental view maintenance is to compute the changes to a view given the changes to a table. And if you take this definition, an incremental view maintenance system is a streaming system. It's not something that does a one-shot query for one change. You have to think of it running forever. And if you think of it running forever, then it's much cleaner and you get all these nice properties of how to optimize it. And almost any query you can think of, at least in the relational model and the data log model, has a nice, efficient incremental implementation. And the incrementalization algorithm is actually trivial. Incrementalize each primitive operator in the query. So we build all this stuff as open source. So if you have any incremental view maintenance problem or any streaming problem, I think you should try to give a try to our system. Would be very delighted to help you. The documentation isn't there as complete as you like, but we are working on it. So this is the picture you should keep in mind. Databases, incremental view maintenance, and streams, they are one and the same thing. You can't separate them. And if you think of it this way, everything becomes much simpler. I'll be happy to take more questions if I have time.
Thanks for the presentation, Mihai. We have a few minutes, I guess. So if people have questions,
I have one question. Well, I have many questions, but I'll ask one. Mihai, I know Frank McSherry is on your co-author list, and he wrote differential data flow, which generalizes this concept of incremental computation further than anyone I've seen, because he can do things like compute transitive closure of graphs, which is an incremental computation, and do that over streams. Is your system, in other words, it's incremental in 2 dimensions simultaneously? Is your system capable of evaluating those kinds of computations?
So the short answer is yes. So we can do the transitive closure equally efficiently. So let me give you just a little history about how this came about. So first of all, I was a colleague of Frank McSherry at Microsoft Research for 10 years. We worked together on some things. And then at VMware, we started a system called differential data log, which was based on differential data flow, which is the framework that Frank built. And we started that was using several VMware products. And it's also an open source project, by the way. But we started pushing the envelope of what you could write in the data log. Data log is actually a very inflexible language. If you want to do just data log, it's perfect. But as soon as you want to do something like group by or aggregates, it becomes a mess. The syntax is just not extensible. And we started thinking about how we wanted to do this kind of computations, including streaming computations using the delay operator. And that's when we realized that this theory explains what differential data flow does in a very modular way. So this theory is both more and less than differential data flow. In differential data flow, the time notion is actually more complex. It's a lattice. They allow times that can be compared only partially. Times are only properly nested for us. We allow lexicographic sorting for times. But that's enough to express everything that we've seen in practice so far. So you can definitely do recursive and fixed point queries using lexicographic times.
That's great. The lattice time was it was so complicated that it was kind of in danger of collapsing under its own weight. So I think if you simplify the idea of time, this makes it a more usable system.
And we'll have one more benefit, because we have this theorem that says that the query is an incremental query is the composition of the components. This is the core theorem, which doesn't apply to differential data flow as it is. So it's very easy to add new operators to the mix in this framework. Maybe it's possible there too, but you have to think very hard about the time in that system.
Yeah. Thanks, Mihai. This is very interesting work. Thank you for sharing with us.
There's one more question in the chat if I have time.
Yeah, go for it. It's an interesting presentation, and it's a pity to interrupt in the middle. So,
okay, so the question is about aggregates. So how do you do average or standard deviation? Okay, so it turns out, okay, so let me start with count. So turns out that count is actually a linear query if you work on Z sets. You essentially just add the weights. That's what the count is of a Z set. And sum is actually a weighted count, where you multiply each value with the corresponding weight and add them up. This is what you would do for a multiset, right? So think of the weights being how many times the row repeats itself in the table. And both count and sum are actually linear queries in this framework. So they're actually fully incremental. You can just tell me what you changed in your table, and I'll change what changed in your count or in your sum. So that is true if you think of the queries as functions from tables to numbers. But in general, the output shouldn't be a number, it should be another table. That's how. That's why SQL is composition. It's a table with one row which contains the result. So it turns out that an aggregate is a composition of two more primitive queries. The aggregate itself, which is linear, and then building this table, which is an extra step, which is not linear. So that one you can do by brute force, but it's only one table, one row table, so it's not too expensive. So what do I mean by brute force? So if you have an operator that you don't know how to incrementalize, you can always use this definition. So you can add any operator you want to the mix, and to compute this incremental version, you will just integrate to rebuild the whole collection, apply the operator, and they differentiate. So there is a fallback if you don't know how to build something in incremental. So, and average is just two linear operators followed by a post-processing step, which is not linear, but it's very cheap to incrementalize using this approach. And standard deviation also works in the same way. You can do the sum of the squares, the sum. These are both linear aggregates, and then you have some post-processing step, which is not linear, but it's still very cheap. Some distinct aggregates are more expensive because they have to apply the distinct operator before they aggregate. But it turns out that the distinct operator is also efficiently incrementalizable. I didn't explain how.